Hey there, students. What I'd like to do in this video is show you how to use StatCrunch in order to take paired sets of data and come up with the regression line or the regression equation that's linear, and to decide whether to use that or not when trying to make an estimate or a prediction. So we're looking at number 37 on homework number 13. And it states that the data show the chest size and weight of several bears. Find the regression equation, and they've got a spot for it here, letting chest size be the x variable. Then find the best predicted weight of a bear with a given chest size. Is the result close to the actual weight of 495 pounds? And it wants us to use a significance level of 5%. So we can always come up with a regression line based on any paired data set. But the significance level tells us whether we should use it or not. It has to be good enough to use. It has to be a good enough match to the data to use it. And if it is, then we should use that to predict the weight of the bear. Or if it isn't, then the alternative is to scrap the linear equation and just take the mean weight value to predict the weight of the bear. So first we'll open up this data in StatCrunch. And we only have 6 data values, so it's not a real big data set here. But to come up with the regression line, we're going to go to Stat, Regression, Simple Linear. Then we're going to choose the chest size for X, as the problem indicated, and the weight for Y. And there's some stuff here about the null hypothesis, but the defaults here will always work for our problems, so we're just going to compute. So we get a box with a bunch of results, and part of what we have here as our result is the regression equation. And they give it up here where we have weight in pounds is equal, and then they have a constant plus a multiple of the chest size. And so we want the constant and the multiple of x. Those are also listed a little bit more clearly and separately here. The intercept is the constant value, and the multiple of x, the coefficient of x, is the slope of the line. And so we can use these, or from the equation, they're the same, and transfer here. In this case, they want them both rounded to 1 decimal place. I have seen some of the problems where they actually specify to round the constant to 1 place and the slope or the coefficient to another place. So watch carefully what they want you to do with the rounding here. But just to 1 place for the constant, I'm going to have negative 32.1. And then for the coefficient, I'm going to have 11.3, both rounded to 1 decimal place. So that's the regression equation. Now it says, what is the best predicted weight of a bear with a chest size of 51 inches? So one way to get a predicted weight is to take the 51 inches, which is a possible x value, and plug it into our regression equation, do this arithmetic, and get a value predicted for y. But we only want to do that if this is a reasonably good fit, if there seems to be a linear correlation. At the 5% significance level, we would need the p-value of this sample to be below 5%. That's also provided here. And in this case, we see it is. We would use the p-value that's on the slope line, and that's the test statistic as well. And so we have something that's a little closer to 2.5%, or actually, no, it's an extra 0 in there. That's below 1%, 0.25%. And so that's well below the 5% significance level. So that means we do have a linear correlation here, and we should use the regression equation to make our prediction about the y value. Now, we could also double check this by looking at the scatter plot, and that you can do by clicking on this right page over to page 2. This is 1 of 2. And on page 2, we see the scatter plot. And you can see, even though there's one point here far away from the others, the line fits all the data pretty darn well. And so this is a good linear correlation. You can also see an R value is like 95%, 96% R value. So that's a good value for a strength of the linear correlation. All of these assessment parameters are suggesting we should use this to make our prediction. So the way we do that is I'm going to plug in a value of 51 in for x, and then multiply by the coefficient and add the constant. So I got my calculator here. I'm going to do 51 times 11.3 plus 32.1 with a negative sign attached. And so my predicted value is 544.2. It says round to 1 decimal place. And that's exactly where we got our data value. And so if I plug that in and check, that's what they want. And then it finally asks, how does this compare to 495 pounds, which is close to the actual weight? Where is 51? I'm not sure where they got that. But nonetheless, if we compare it to a 495-pound result that they got from somebody, it seems pretty high. It looks like it's over by almost 10% over. Do I want to say that's very close? Not really. It's exactly the same. Definitely not. Close to the actual weight, or not very close. I'd say not very close. There we go. But nonetheless, a little bit of a judgment call at the end of this problem. Now, let's also take a look at the next problem on the list, because it looks pretty much the same. So if I look at this problem, they also give us paired data. They want the linear regression equation. And so let's see how that goes. Listed below are the systolic blood pressure measurements in millimeters per hectogram, I think that is, or millimeter hectograms, obtained from the same woman, meaning from right arm and left arm, I guess, at different times. Find the regression equation, letting the right arm be the x value. Find the best predicted systolic blood pressure in the left arm, given the systolic blood pressure in the right arm was 85. Use a significance level of 5%. So this is very, very similar to the bear chest size versus weight problem. We'll open the data in StatCrunch. And again, a small data set, only 5 values here. And so to come up with the equation, I'm going to go to Stat, Regression, Simple Linear. I'm going to select right arm for X and left arm for Y as the problem indicated, and compute. So in this case, we get our linear equation, and so they also want both of these rounded to 1 decimal place. So it looks like this first one rounded to 1 decimal place would actually be, the constant would be 72.0 if I round it off correctly, hopefully. And then the slope, or the coefficient of x, is 0.97, which would basically be 1.0. If I rounded that off to 1 decimal, the 9 would go up, and I'd get that. Okay, so we still got the linear regression, regression equation. Then it says, given the pressure in the right arm was 85, the best predicted model for the left arm is what? So the question again is, do we take this 85 value, stick that in for x, and see what the equation predicts, or do we not? Well, in this case, we got a p-value of 6.5%, and we're supposed to have a significance level of 5%. So that means that we are not going to accept the idea that there is a linear correlation and that this is the best model to use. If I look at the R value, well, it's decent, it's 85, but again, we're supposed to be working with a 5% threshold here. If I go over and look at the data, it actually doesn't look very good for linear, because even though they're kind of on both sides of the line, it almost looks more like they're supposed to be a big curve, because in the beginning and the end, they're all on one side of the line, and then in the middle, they're on the other side. So this is definitely not convincing. But specifically, we didn't meet the threshold of 5%. So what do we do if we scrap this linear equation model? If that's a bad model, then the book says instead, if you're not going to use that, just use the average value as a predictor. So if I'm trying to predict the left arm value and I'm just ignoring the right arm value, I want to get the average of these left arm values. So I'm going to toss this out. And to get the average of the left arm values, I would go to Stat, Summary Stats by column. And I would choose the left arm and say, well, what's the mean? And I get 159. So I'd say using that, I'm going to predict 159. So if we had used the equation, we could kind of see if that would have given an answer that they would have marked wrong, since they like the average value answer. Well, if I put in the value of 85 for x into the equation, 85, I'd multiply it by 1, and then I would add 72, and we get 157. So it wasn't terribly off. You could see the line wasn't a disaster. There was an 85% R coefficient, but it's not 159. And if I think we put in 157 from the equation, we would have been marked wrong. And the reason is we're not supposed to use the equation if we can't surpass the significance level of 5%. We're supposed to just use the average value. So there's two different problems. The one previously, we did use the equation because we beat the 5% significant level, and that gave us our guess. And in this one, we still gave the equation because they asked for it, but because we didn't beat the significance level, we abandoned it and instead just used the mean value as the best predictor for, in this case, the left arm blood pressure. So there's an example of a couple of problems from your homework, both of them in which you need to come up with the regression equation. And also I used a couple different problems to illustrate that sometimes you come up with it and you use it, and sometimes you come up with it and it's not good enough, and so you don't use it. Keep up the hard work, and best of luck.